je devais résumer la bibranche avec vous aujourd'hui, je dirais que c'est d'abord des rencontres. Des rencontres entre étudiants appartenant à différents laboratoires, différentes entreprises, mais aussi avec des chercheurs venant du monde entier. Nous accueillons tous les étudiants appartenant au domaine de l'électronique, au sens large. Nous donnons la possibilité à ces étudiants membres de créer leur réseau professionnel dans des domaines qui leur tiennent à cœur. Être membre bibranche, et donc membre I3E par extension, cela vous donne beaucoup d'avantages. Notamment, vous aurez accès à une grande librairie d'articles de conférences en électronique, mais aussi à l'actualité des dernières technologies et aux événements organisés par les entreprises de pointe. Mais avant tout, cela vous permet de faire partie d'une des plus grandes communautés scientifiques mondiales. Et tout cela pour seulement $20. Sur le campus bordelais, on organise des événements à peu près tous les mois, sur place ou sous forme de virtual event, au cours desquels on a des invités tels que des chercheurs. Mais on permet aussi aux étudiants du campus bordelais de transformer leur projet d'études en projet I3E, en ayant un soutien financier, et nous les accompagnons aussi dans l'écriture d'articles scientifiques afin qu'ils aillent en conférence par la suite.
Être à la bibranche, c'est faire partie d'une équipe dynamique et soudée pour promouvoir la science.
Pour moi, la bibranche, c'est l'occasion et l'opportunité de changer son quotidien d'étudiant. C'est l'occasion d'organiser tout plein de choses, des séminaires, des journées thématiques ou encore des concours technologiques autour de divers sujets scientifiques.
Rejoins la bibranche.
La bibranche.
Donc rejoignez tous la bibranche.
Únete a la B-Branch.
It's a B-Branch, bye.
Unisciti alla B-Branch.
Welcome everyone to this new live stream of the B branch from Bordeaux IMS laboratory. Today we have the pleasure to be with Paul Jespers from Université de Louvain. This talk is a special talk because it's the first talk of the new B branch team of Bordeaux. So this will be the first one for us. So before we start the talk, I'm going to quickly introduce our guest, Paul Jespers. Paul Jespers was born in Belgium in 1929. He received the engineering degree from the University Libre de Bruxelles in Belgium in 1953, and his PhD degree from the Université Catholique de Louvain in 1958. He is Professor Emeritus of the Université Catholique de Louvain and former head of the Microelectronics Division. His present activities include MOS analog circuits, digital to analog and analog to digital converters, GM over ID sizing methodology, as well as low power application. Today's talk will deal with a sizing methodology that takes advantages of parameters extracted from pre-computed lookup tables derived from SPICE. Features like gain, current consumption, and so on can be evaluated and optimized without the need to run repeated simulation. Professor Jespers, thank you for being with us today. The floor is now yours.
It's a pleasure. Thank you. Do you hear me?
Yes, we hear you clearly.
Okay, good. I want to congratulate you first for your presentation. I mean, the film I've seen before is very, very professional. It's very well made. Thank you. Very good.
Yeah. So it was
So
made
I'm going.
It was made by the Video Association of the Answer Matmeca. So the quality is there.
Super. Okay, I'm going to open. Okay, how does it work? Do you see my screen?
Yes, we can see your screen clearly.
Okay, so I can start, I suppose.
Yes, you can.
Okay. Well, good afternoon. It's a pleasure to address the Bordeaux IEEE student branch. I'm going to introduce a talk about the systematic design of CMOS analog circuits. In fact, this is work that has been done together, Boris Merman and me. Boris Merman is professor at Stanford University, and I am professor emeritus at the Université Catholique de Louvain in Belgium. Unfortunately, Boris is so busy. He told me, "Please do it." I cannot help. I cannot help doing it, but okay, I take the care of this. Then. Okay, what is it about? What are we going to talk about? We start from something that you probably realized since a long time. You're using textbooks, and you can find a lot of things in textbooks on circuit design, examples. What you don't find is how to conceive them, how to size them. Analyze a circuit is something you will find easily. There are many, many books. Sizing, there are not many. And you will understand why. This is a problem. Every engineer going in industry is faced with this problem, has to solve it himself. And so what I'm going to present here is a tool, or let's say a methodology, that is the intended of it is to promote the systematic design by using analytic methods. Okay, I'm going to take an example, and for the whole conference, there will be one single example. In order to get really involved with it, you see everything numerically. You're going to see how we propose what it is exactly. So, what is this example? I think most of you are working in radio frequency. So I took an example, the simplest example I could ever imagine. It's a common source transistor loaded by resistance and by capacitance. It's a very classical thing. It's very elementary. It's not typical of radio frequency, but you see these things in radio frequency. And this is a circuit which is supposed to work under a voltage of 1.2 volts. And the point is the following. This circuit has a frequency response, which is, if you can see my pointer, when frequency response is classical, you have at low frequency a constant gain. And then past at the cutoff frequency, the capacitance is driving us more and more current. And at high frequency, all the current is flowing in the capacitor. So the resistance is not, we don't have to take account of the resistance anymore. We have a frequency response which is dropping at minus 20 dB per decade, you know, all these things. And what is interesting is the point where we cross the 0 dB axis. I call this FU. Often it's called the gain bandwidth. So now, what are we going to do? Well, we're going to try to synthesize this circuit in such a way that the gain bandwidth be equal to 1 gigahertz. But that's not all. We want, in the same time, to maximize the gain. So the trick is really, how are we going to determine the drain current? which width are we going to consider, and gate length, and what will be the value of the load resistance here, so as to be sure that we, first of all, get the adequate gain bandwidth of 1 gigahertz, but be sure that we cannot do better than what we have done here in order to maximize the gain. It's not a very large gain, you know, these high frequency circuits. Especially if you load the transistor with a resistance, you cannot expect a gain that is much larger than, say, maximum 10, 15 or something like that. But that's typical of many high frequency circuits. So that is really the problem. Okay, now what are the elements, what do we have in order to solve this problem? I'm going to consider technology, 65 technology, which is the one in the book. And I assume that we can use the quasi-static model. That means that we are working at frequencies that are not so low, but not thousands of gigahertz or things like that, of course. I'm going to give more precise idea what it means, quasi-static model, just wait a minute. What else do I know? Well, the low frequency gain is given by this expression. This is very classical analytic expression. And the gain bandwidth product, this point here, is given by omega u. The angular gain bandwidth product is equal to Gm, that the transconductors of the transistor, divided by the load capacitance. So I remind what we are going to fix is the drain current, the gate length, the width of the transistor, and the value of the resistance, load resistance. Okay, now we're going to work with real transistors. I told you 65 nanometer technology. Real transistors are rather complicated things. What you see in this representation here is the drain current versus the gate to source voltage. The drain current is represented in a log scale. And the reason I do that, it's not common, I know, but the reason I do it is because I want to show you the subthreshold current. Usually, we use the quadratic model, that is the simplest model, and it's not a bad model. You have an example here of the quadratic best fit model, but the black current that you see here is really the drain current of a real transistor. So I have tried to find the best fit with a quadratic model, and it's not so bad, especially in this region. Usually, it's common to say the quadratic model is a good representation as soon as the threshold voltage exceeds the gate voltage exceeds the threshold voltage by about 0.2 volt. That, you see, it's about the case here. It's not so bad. We have, of course, the problem of velocity saturation, which is not taken into account here. The values of the threshold voltage and nu-Cox are those which I computed in order to get the best fit. But the big problem is, as you see here, that of course, when the gate voltage gets equal to VT0, the current is 0, and below there is no current anymore. Whereas in reality, there is a lot of current here, and the transistor has a characteristic which is almost a straight line. In fact, this is typical of the so-called weak inversion mode of operation, whereas here at the right we are in the strong inversion mode of operation. In between here, in blue, you see a region which is called the moderate inversion, where in fact none of these simple models fit. The quadratic model is completely wrong, And the subthreshold model, you have an example here of the weak inversion. Is almost like an exponential. It is like a bipolar transistor. In fact, in weak inversion, a MOS transistor is like a bipolar transistor. There's not much difference, except this factor N you see here, which is the subthreshold factor. The point is that none of these two equations is okay in order to represent what happens in the central region. And nowadays, most circuits operate in this region, in the so-called moderate inversion region. Why? Well, because it gives us the best performances regarding gain, bandwidth, but in the same time, power consumption. If you go to strong inversion here, you lose gain, you absorb a lot of current. If you go in this direction, the current is very low, your gain is very large, but the frequency response is poor, whereas here it's high. So moderate inversion is a kind of compromise. The point is that you don't have any equation, simple equation, let's say, any simple equation that can be used. So we go back here. Okay, what equation can I use? What are the parameters I can use in order to solve that problem? Well, in fact, the question is the following. Elementary basic models, we cannot use them because they ignore important second-order effects. A very important one is DIBL, drain-induced barrier lowering. Drain-induced barrier lowering. But you have other effects, channel length modulation, mobility degradation, threshold voltage roll-off, and there are others. So all these effects have an increasing impact on the characteristics of the transistor when you go to very short channels, and when you work in moderate or in weak inversion. So you cannot really use these simple models because they don't take into consideration all these important effects. On the other hand, advanced models exist. BSIM, PSP, etc. These are advanced models. These are the models which are used in advanced simulators. SPICE, NXP, for instance. They use these models, which are, I would say, almost perfect. Not exactly, but they are very close to reality. The point is that they use a large number of equations, you know that, a number of parameters, etc. So if you try to do what we could do here with elementary basic models, you will try to do it with these models. You can't because you have too many equations, too many expressions. So there is no answer. And the fact is, since there is no answer, what do we do? And this is good practice. Everybody does it. In industry, this is the normal way of working. You have a circuit to design, you know the specifications. Well, you're going to establish, you're choosing a circuit first, and then you're going to size that circuit. That's what is called hand calculations here, not necessarily by hand, but first estimates, which are based on what is available. For instance, the square law model, okay, you can try that. And then you go to a simulation, SPICE, for instance, which is using models like BSIM, PSP, which are much more elaborated than the square law, and you will see what is the result. And what comes out of it is that the square law-driven optimization will be very, very far from the SPICE results. What you get is far. How can it be? If you use this and use the quadratic model, you ignore simply the weak inversion, moderate inversion, etc. So what are we doing then usually? Well, usually what is done is, okay, you get the first result. It's not a good one, but it's not so stupid as well. So you try again, and you say, okay, this effect is probably the length of the transistor. I should increase the length of the transistor. Let's try this, and I go again, you do some calculations, and step by step, you find the final result. And this is the way it's done almost everywhere. This is an effective way, and the purpose of this talk is not to say this is bad. I want to say this is a good way to do it, but we want now to try to do it on a more analytic way. What can we do that for? And this is the next. If we could do this first step here, the hand calculations, with real characteristics, then the result would be good at once. Okay, well, the simulator here is using models. Can we not use this model and change this model, this complicated model, but change it into something we can use directly in order to to make our first hand calculations. And this is by means of lookup tables. So we're going to use lookup tables, which are driven by SPICE, which is derived from BSIM PCM. What it means, you're going to see in the next slide. In fact, this is the main part of the presentation I'm going to do. So, okay, what are those lookup tables? I'm dividing them in two levels. I'll start with the first level. And okay, this is a little bit of formalism, but we have to go through in order to go to the next slides. In fact, this is a MATLAB expression which is using the data developed in the lookup tables. So it's done the way the lookup tables are set up. I'm not going to discuss. I will just give you some references if you're interested. But suppose this is done. So I'm connected to the lookup tables through MATLAB. And this is the instruction of lookup table, which allows me to determine the drain current of the transistor. In this case, it is an N channel. What I'm looking for is the drain current. And there are here 4 parameters, respectively VGS. VGS, I know it, okay. VGS, the gate to source voltage, the drain to source voltage, the source to bulk voltage, and the gate length. So these colored data here represent what we're interested in, the drain current and the data. These are not the only data we are going to consider, but the black values are the values that I'm considering for the given example I will consider. Now, just a few words about the ranges. VGS, for instance, VGS is a vector. In MATLAB, it's a vector. And it's a vector which goes from 0 to 1.2 volt in steps 25 millivolts wide. So this is a structure. If I put, for instance, VGS here equal N channel point VGS, immediately then I'm going to get the drain current for every value here. This is the full range of VGS because the maximum voltage, maybe I forgot to tell that the maximum voltage here is 1.2 volts. Of course, I can put any other voltage, but this is just to show what is the range, what are the ranges. This is for VGS. In fact, for VGS, it's the same thing. The default value, because we have default values as well, is VDD over 2. And VSB, we can have a number of voltages from 0 to 0.8 volt in steps 100 millivolts wide, the default value being 0 volt. The width of this transistor is constant. It's supposed to be a transistor 10 micron wide. So we need something, this is the base of everything in the lookup tables is supposed to be 10 micron wide. This is an important point because we are going to change, of course, W, and I'll show you why and how we do that. Okay, next slide. Well, here you have an image of the representation of that transistor. So the entire lookup table is built on the basis of this kind of transistor, which is a multi-finger transistor, 5 fingers. The width of the transistor is 2 micron. The gate length here is a variable which can change, I think it's here, from 60 nanometer to 1.2 micron. These are all the values you can take, but all these values you can interpolate as well. You're not stuck to these values only. Okay, I think to this point, that's all I want to say about this transistor. And let's take an example. Suppose we want to compute drain current versus VGS, given the following data. For the gate lengths, we're going to consider 2 gate lengths, 100 nanometer and 500 nanometer. For VGS, I'm going to consider 5 values from 0.3 to 0.7 value in steps, 0.1 volt wide. And for VDS and VSB, I'm using the default values, respectively 0.6 volt and 0 volt. So the expression, I have to fill in here is ID, lookup, N channel. What I'm looking for is the drain current. VGS, okay, I write VGS because it's defined here already in MATLAB. L is defined. This is a vector. This is also a vector. So what I'm going to get is a matrix. And VDS, VSB you don't see them here because they are the default values. And the output I get is here. So this is L, this is VGS. For instance, this point here corresponds to 100 nanometer and a VGS of 0.3 volt, etc. And the values you see here are represented on the characteristics. Of course, they are exactly on the characteristics with the 2 gate lengths. And remember, this is for a constant gate width of 10 micron. So you see this, the mechanics. That's the way you get the drain current or any other variable, because this is going to be the same thing for the transconductance, the output conductance, and the parametric capacitances, for instance, CGG, CGS, etc., etc. Okay? Please, if you have questions, don't hesitate to interrupt me or to call the center office, and they will send me the question. I will be pleased to answer during the presentation. Meanwhile, I'm going further. Lookup tables, level 2, and here things become more important. In fact, we are going to assume, this is a basic assumption, that all the parameters that we consider vary like the width. In fact, this is true, especially in analog circuits, because you have exceptionally small transistors. All transistors, especially in high frequency, are very wide, and the proportionality is guaranteed. Of course, I can say that, and you're not obliged to believe me, but I don't have time to go in detail. I can show that this is working effectively. All what I can say here is that we take measures in order to make this assumption true. For instance, suppose you design another transistor with a width, let's say it's double, for instance, double. Well, what we are going to do is simply to double the structure, connect to this transistor another one, etc. Okay, it's not necessarily double, it's not necessarily a multiple. What happens then? Well, if it's not a multiple, we are going to associate a number of fingers in such a way that the width of the transistor be as close as possible to 2 microns. So you see, any transistor or any W will be derived from this model, and its width will be similar but not equal to 2 microns. So there are discrepancies, there are differences here, and they have an impact on the characteristic. They make this this assumption not exact, of course, but it's possible to show, this is something which is shown in the book, as long as you have a transistor with a W, which is in this case larger than 10 micron, you will not see the difference. And even if you go below, but okay, if you take a transistor with the width of 2 micron, of course, that doesn't work. So this is not for digital design, this is for analog design, where you need very wide transistors, and mostly this is the case. Okay, now this second category of lookup tables, what do they contain? Well, they contain parameter ratios. In fact, ratios of the parameters you have seen in the first level. So for instance, ID over W, that's the drain current density. Or GM over ID. GM varies like W, ID varies like W. And so all these parameters you see, ID over GD, etc., all these parameters are parameter ratios which are width independent. They are assumed to be width independent, which is going to introduce a kind of degree of freedom that we're going to use later. Now, I would like to say a few words to say something about every ratio you see here. The drain current density is something obvious. Everybody knows what it is. Transconductance efficiency is a key element. The early voltage, the intrinsic gain, well, GM over D, that's the gain of the open drain transistor you've seen in the beginning. The transit angular frequency. So let me just take a few minutes in order to review these four quantities and say a number of things which physical thing. Consider it's very important when you do analog circuit design to be physical minded, to see what are these things really representing. Okay, so I start with the GM over GDS, which is the low frequency voltage gain. So it's the gain you get with the stage you've seen in the beginning, but with an open drain. So this is current source feeding the transistor. And here you see, first you see the expression, which is AV0 lookup and channel, GM over A. That is the way to call the gain. And for the rest, okay, I'm going to consider only default values for VGS and VSB. And I define VGS as the structure, so I'm going to consider the full range of VGS from 0 to 1.2, and the gate lengths that I consider are noticed here. They go from 100 to 400 nanometer, and so this is already a representation that you get of the gain of the transistor, which is in fact extracted from the SPICE simulations, from the models, the most advanced models, the models that you see in the simulator. Well, it's interesting to look at this. When we have VGS here in the neighborhood of 0.6, 0.8, etc., we are really in strong inversion. And we see the gain is decreasing, and this is an effect we know very well. On the other hand, if we are in weak inversion here, maybe that's a point which is less known. I think, well, not so much. The gain gets very large. The gain is in fact maximum and almost constant in some range here in the weak inversion. Then it drops again, but that really, when you go to such small gate voltage, I don't know whether you can still call it transistor. So if you're looking for gain, you say, okay, well, why should we work? Why should we not work in weak inversion? Well, of course, there is a problem that is frequency response, as you're going to see. If you want to have a large frequency response, you have to go here. Your gain is going down. So you see, we are already introducing the idea of compromising. Okay. Well, that is the second point, the transit angular frequency. So we're going to see what is the limit. Well, how far can this model, can I use it for any frequency? The answer is no. Remember, I started saying, okay, we are going to see the quasi-static model. The quasi-static model means that I can use this kind of model, and the transit angular frequency, omega t, is defined as Gm over CZG. What is it? Well, in fact, this is nothing else as the current gain of the transistor. You see, the transistor is shorted at the output, and I'm considering the ratio of the output over input current. And that ratio is, well, the current, just remember, if you start at a very low frequency, the input current is almost zero. Your output current is depending on VGS, but it's way larger than the input current. So you have a very, very large gain, current gain. Nobody is really interested in current gain of MOS transistors, except that if you go to very high frequencies, you see that your output current will stay the same if VGS is not changing, whereas the input current is increasing, and there will be a moment that the input current be equal to the output current. And when you are at that point, you are very, very far in frequency, you're very far. In fact, you are at the limit beyond which it's already over the limit where the QSM is valid. So you can't work with that model, you can't work with methodology beyond this value. In fact, we are going to use the conservative rule of thumb, which is to assume that the model we use will be used never beyond FT over 10. So I'm going to introduce this. Now, this current gain, you see here a number of examples. Again, you see it's the classical expression, lookup and channel, Gm over the CGG, that's the omega t, and then divided by 2 pi, because I want to look at the frequency. And this is a representation, again, versus VGS, considering the same gate length as before. And of course, if the gate length is getting small, then I'm going to get a very good FT. In fact, with you see at in strong inversion with a VGS of 1 volt, a gate length of 100 nanometer, I will be above 70 gigahertz. That's for FT. Remember, don't forget, we are going to work at FT over 10. So the model I'm going to use is valid. I'm sure it's going to be valid until 7 gigahertz. Of course, if I could work with smaller gate lengths, I will push up this FT. It's possible to, this is not a very advanced technology. Nowadays, you have 20 nanometers, even less than that. You can easily, you would have maybe 20 times more gain bandwidth, some 25 approximately. So you see, you can have very, very large bandwidth and still be able to use the QSM. If you can't, you have to go to scattering parameters, but that is much more, that's different. You cannot use this method with scattering parameters. Okay, next point. I think the time is going, I'm going to skip this one because it's not a very useful slide. But this one is much more important, transconductance efficiency, because you're going to see that many things are based on the GM over ID. On the right side here, you see the characteristic ID over VGS we have seen already. Strong inversion, moderate inversion, weak inversion. What is GM over ID? Well, GM is ID, 1 over ID. GM is the derivative of ID versus VGS. But this is nothing else as the derivative of the log of ID. So I put this equation because what it shows is that if I draw ID versus VGS in a semi-log plot, all what I have to do in order to visualize GM over ID is to take the geometrical derivative. Here I have a constant derivative, which is maximum, you see it here, and then it goes down like that. In weak inversion, it's maximum, in strong inversion, it's minimum. So what GM over ID represents is in fact nothing else as the derivative of the semi-log scaled ID versus VGS represent current. Another interesting point here, the maximum here is given by the slope of the weak inversion model. You have seen the exponential model that I used there for. You can show that the maximum GM over ID is equal to 1 over NUT. And I show this because if we were working with bipolar, N would be equal to 1. And you would have 1 over UT. So this is an absolute maximum. Your GM over ID will never be larger than something like 38 Siemens per ampere. For MOS transistors, and this is due to the fact that MOS transistors have 2 gates, a front gate and a back gate. So if I short the source to the substrate, I have only one of the 2 gates working. And that explains to some extent why we have this N here. This N is the factor which is comprised usually between 1.2 and 1.5. So all what I wanted to show here is that the maximum is going to be necessarily somewhere between, 22, 30. It could be more, it could be less, of course, but it's something like that depending on N. Only, well, SOI, they have a smaller N of 1, and bipolar, well, N equal to 1. Okay, so what do we know about GM over ID? Well, this is a characteristic curve. There is a maximum here, and we can also represent GM over ID here. For this, you see there are 2 transistors, a P channel, an N channel. I also consider several VDS values, and I could consider, it's not done here, several source to bulk voltages. And you see, all these curves look the same, look almost the same. Why? But simply because all transistors have characteristics like these. They all have a more or less quadratic shape here and a more or less exponential here. And then you have the moderate inversion here. You see this moderate inversion, this is going to play a very important role. Now, what is this? Why do I show this? Because it's tempting to say, I would like to size the circuit starting from the mode of operation. For instance, if I say 15 Siemens per ampere, I'm typically in moderate inversion. And I define this as my starting point. If I like to do that on the basis of VGS, it would be much more difficult because there are a lot of values possible here. So of course, I can control the mode of operation with VGS. That's obvious. But I'm never sure. Just take any characteristic and say, okay, for this transistor, I'm taking VGS equal to 0.55. I'm probably in moderate inversion. But suppose that you introduce a voltage between the source and the bulk. All these characteristics are going to shift to right here. So you will need a much larger VGS. How are you going to say, okay, I want to be in moderate inversion, I want to look what is happening in moderate inversion? It's already more difficult. So why not saying, okay, let's reverse things. And let's give to GGM the driving rule. And we're going even to forget VGS. We don't need VGS. We are going to work with GM over ID only. Okay. This is a slide which is here to explain where you can find information on how to set up these lookup tables. But now I can give you copies of this if you want. What I'm going to do now, the second and last part is, okay, let's go back to the example and solve our problem with the tool what we have now. So remember, we have a common source transistor loaded by a resistor, a capacitance of 1 picofarad. And what do I have? Well, first of all, I'm going to look at the gain. The gain AV given by this expression. And look what I'm going to do now. I divide everything by ID. So that is a good way to make to appear to have GM over ID here. Of course, I'm going to introduce GS over ID, GDS over ID, which is one of these level 2 functions which is available. On the other hand, here, that is just by chance, I have an expression 1 over RL times ID, which is nothing else than the voltage drop across RL. So I can rewrite this expression the following way: GM over ID. Here, what I have is the reciprocal of the voltage drop across the resistor, and this is, in fact, I didn't speak about that. This is the reciprocal of the so-called early voltage. But okay, we don't need this concept now. Okay, we have this expression, and now we're really going to start solving our problem. To begin with, I'm going to start step by step. Suppose I'm choosing GM over ID and L, and I want to find the gain. So this is not synthesis, this is kind of analysis. But it's a way to go step by step. Okay, you will see I will take, for instance, 15 Siemens per ampere, and let's say here, 0.1 micron gate length. I will rewrite the expression here. GM over ID, okay, let's say 15 Siemens per ampere. GDS over ID, well, I'm going to use the tool I have, Lookup, NCN, GDS over ID, yes. And you see here, instead of previously we had VGS, etc. Now I can use as well GM over ID as one of the driving variables. So I still have 4 variables. 1, 2, 3, 4, and I can evaluate the GS over ID, which correspond to this GM over ID, and the VDS, which I choose. In fact, what I'm going to do is consider VDS as a parameter. So, because I don't know which one is the good one, should I take 0.3, 0.4, or 1. Okay, if I take a very small voltage, the transistor is short-circuited, so I have no gain. If I take a very large one, the transistor is operating in good conditions, but the resistance is very small, and I have very little gain. So there's an optimum somewhere. And in order to find that optimum, I'm going to work here with a parameter, and VDS is a parameter. It's going to be the general parameter for the problem here. Okay. Knowing GM over the ID, GDS over ID, and knowing VDS, I know everything. I can find the gain here. Okay, let's do the computation. What is the result? The result is here. So this is for the values that considered 15 Siemens per ampere for GM over ID and 100 nanometer for L. And here you see the gain, how the gain changes with VDS. So I know already there is a maximum here, and I should work in such a way that VDS be equal here to 0.4 volt. That will give me the maximum gain. I still don't know which current, which value of resistance, but I'm for sure this is the best value of VDS. If I go to too low value, I have the saturation of the transistor. If I go to a large value, I have the output, which is almost shorter because the resistance is too small. Okay, that's the first step. Okay, now I can compute, I can evaluate with the, I have everything, it's just MATLAB, it's computation tricks, it's easy. I can find the maximum, which is a gain of 7. The VDS max was not exactly 0.4, but you see the value here. And with these values, I take the opportunity to have these values in order to compute already the drain current density and the FT. They're not needed. Well, they are needed because I don't have the, in order to know the drain current, the size, etc., I need to know what is the drain current density. This is fixed. Once all these things are fixed here, the drain current density is known. It's in fact equal, as you can see, to about 8 microamps per micron. And just to check, let's compute FT. You see that the FT that we obtain is 16.3 gigahertz. That means that we are still we are using legitimately the QSM model, because a maximum would be 1.6 gigahertz. We're working, the maximum frequency we consider is 1 gigahertz. So that's okay. We can go on. Okay, second step, high frequency, and then finding the value of ID, etc. So what I'm going to consider now is the load, the capacitive load here. The gain bandwidth product is 1 gigahertz. I consider a 1 picofarad capacitance. Well, you remember we had the expression FU equal GM omega U, please, omega U GM over CL. Okay, so I can find GM, which is 2 pi times, this is the angular gain bandwidth, times CL. So I can find the GM. Since I know GM over ID, and I know GM, I can find ID. And I already computed the drain current density, which gives me W. And now using this last expression here, I can find R. Okay, so now I have everything. Everything, yes, only if I consider the GM over ID and the gate length that I consider, that I choose before. So really the problem is it's something different. What is the problem? The real problem is the following. I want to optimize these things. So I'm going to consider not a fixed GM over ID, but a variable. You see, I go from 5, which is really strong inversion, to 25, which is really weak inversion. And I'm going to consider several gate lengths here. The rest is just MATLAB mechanics. I'm going to redo the same computation. All the expressions that you've seen before here, I'm reusing them. But now it's with vectors and matrices, is nothing very special. And what I get finally is the following. This is a graph which represents versus GM over ID and L, the gain that I can obtain and the FT that I obtain accordingly to the choice I'm making. Okay, for instance, I think I have to go back here. You see, I've considered several values of gain. Yeah, I think I was not very clear. Please excuse me. I'm going to give you a little more explanation here. I'm going to consider 5 gains, 5, 6, until 12. And I'm going to consider here 3 gain bandwidths from 500 megahertz, 1 gigahertz, and 2.2. This is an error. It should be 1.2. It's an error, excuse me. That should be changed. Okay. So for every value here, I can find the contour. So these are the constant, what you see here, constant gain, is constant gain 5, constant gain of 10 versus the gate length and the GM over ID that I consider. In red, you have the same thing for constant FT, 500 megahertz, 1 gigahertz, 1.5 gigahertz. This is correct. Okay. So what can I do with this plot? Well, this is just a visual representation that shows me that if, for instance, what I am interested here is the 1 gigahertz. If I walk on this red curve here, I have an FT which is not going. I have a gain bandwidth which is 1 gigahertz, which is not going to change. Oops. But I see that if I choose, let me put it another way, every point here gives access to a GM over ID and L, which, once they are implemented in the circuit, will give me the correct 1 gigahertz gain bandwidth that I expect. So now I can see that there is indeed a maximum here somewhere, which is the absolute maximum, because there's nothing more I can change. When I go here, I see that I push the gain to the maximum, which is about 8.5, 8.4, something like that, which corresponds to a GM over ID of 18, which is really moderate inversion. It's beginning of weak inversion, but it's moderate inversion mainly. And the gate length is about 110 nanometers, something like that. So in fact, I solved my problem. I have all the data here, which I need in order to implement it. And I know that with these values, we can try. You can go to your cut and try method of evaluating the values of the circuit through the first slide you've seen, when you will be changing resistance, current, etc. Try. The optimum you will find is this one. You know it. Did we gain something doing this? Well, in this example, no, not very much. If you do it with the program directly, which you do it with, you see it here. If you do it with this, it's going to take you the same time about. But with more complicated circuits, but I don't have time to do it, it's completely different. And you can find solutions which are definite solutions, whereas you may have a lot of parameters to look at, which is going to make the task much more tougher. What I want to say, to show you more now, and then I will end because it's almost time, is there is something which is still missing in this example. In fact, I know what is the width is not here, but it should be here. Oh, I should have taken it here. No, okay. Well, sorry. I did not take into consideration the parasitic capacitance at the drain here, the CDD capacitance of the transistor. And in fact, it is in parallel with 1 picofarad here. These transistors are white transistors. The parasitic capacitance, you have to take it into account. If you don't, you're going to have results which are, let's say, maybe 10% off of the result. So I would like to introduce it. Well, that is possible as well. You see it here. I introduce the capacitor. One of the level 2 parameters that I am using is CDD over W. It's exactly the same kind of thing. I already know GM over ID, the VO, I know these things, so I can evaluate the parasitic drain capacitance per micron. So what I'm going to do is, okay, when I compute a GM here, your CL is not what you expected. It's CL plus CDD. So I'm going to add CDD here. Since I don't know CDD when I start, I go with CDD 0. I compute. This is the computation I just made. I find the value of W. Having W, I have a first guess of what is CDD. I'm going to add it to CL. And in fact, if you do this 2 or 3 or 3 times, you get a steady state value. And now you're getting even the W, the R, everything is here. You see it here. This is the final result. And of course, you want to check it. Well, this is a check. This is the SPICE verification. So the circuit, we see the same values here. The circuit is in a feedback loop. Why? Because, in fact, I don't know what is the VGS I should impose there. So what I do is I put it in a feedback loop. This is a low-pass filter, so that the output voltage here is controlled with respect to what I'm supposed to have, is 0.4 volt. And I control the gate in such a way that I get exactly here the output voltage. So in this situation, I know you have, of course, to run the SPICE program, you have to write this in SPICE terms. You have to run this, and then you will see the result. And in fact, I show you the results here. There are true results This is not this is really, it had been really, it's really computation. This is what I expected. This is what SPICE is giving. The same thing for the gain here. Okay, so we got the result, and I said just a few words about VGS. VGS, okay. We did not use VGS. Something is not working here. Okay, I know why. Okay. Strange. You see, VGS, I didn't know it, but it's SPICE who determined VGS. In fact, the whole computation was done without knowing VGS. I didn't know VGS. I didn't need VGS. I'm working with GM over ID. The driving parameter is the mode of operation, not VGS, the mode of operation. Of course, you want to know VGS, but here it's the end value. I compute it using one of the other lookup tables. This is a special lookup table, VGS. You see, it's always the same kind of thing. The data we got, we put in here, and we get the final VGS, which in this case is almost 0.5 volts. So this is the end of the story. So what we have done is set up lookup tables that enable us to estimate a first circuit, which is close to reality, because the parameters that we have been using are the true parameters. They are voltage, current dependent. They are dependent of all the effects, DIBL, etc. Everything is here in the BSC or the PSP model, and they have been turned in values that I can use, numerical values I can use in order to compute the circuit. So that's why you get the result almost at once here. You don't need to do a second run to get the result. So that's, in fact, if you're interested, this is the book which has been published by Cambridge University Press. You will see there's much more in the book here, many more examples, more advanced models. I can just show you this is one of the examples. For instance, for those who are working in radio frequency, you will recognize this circuit. This is a balloon, which is a balloon that has been proposed by Blackmere. It has been published in Journal of Solid-State Circuits of June 2008. And it has a symmetrical output. You enter asymmetric, your output symmetrical. Your input impedance is 50 ohm. The thermal noise of the common gate stage is completely annihilated. That's the idea. In fact, this circuit, the interesting point in this circuit is that it changes the noise of this transistor in common mode noise, which is ignored by the rest of the system. So the only noise source that you have is this transistor here. And using the same method, we can evaluate which is the noise and try to optimize the design. And I'm not going to do that. We don't have the time to do that. I didn't intend to do it because it would be really too long, but this is to show you the result. Here you have the MATLAB output and the SPICE output, and you see that the minimum noise, the noise figure of 2.3 that we compute, corresponds very well with the SPICE simulation. So this is just to show you, okay, you're not obliged to solve small little problems. You can, in the book you will find an LDO, white current, white swing, high impedance, current mirror, and LDO operation amplifiers and things like that. So, okay, I think I will stop here. So thank you for your attention. Okay, so this is the end of my talk. Can we return to?
Thank you, Professor, for your talk. It was really interesting and very didactic. I personally really enjoyed it, especially as a new designer. We have now several questions in the chat, I believe, so I can read it to you and you can answer them. So the first one is from François Rivet, which deals with artificial intelligence. So what is the most efficient for circuit sizing, simulation iterations, designer experiences, or artificial intelligence? It's a bit of a general question.
I think I will be very careful. My answer would be use these techniques with artificial intelligence. It's possible. I don't have the experience myself, but artificial intelligence is able to do what I've been doing here. So if you combine things, I think this will be the most efficient thing. It's not the only reason why we should consider this, because you have to consider also other, in a design center, for instance, the same design may appear after a few months and the director is coming and say, okay, change this because I need my gain bandwidth has to be larger by a factor of 2 and I want less current up. So if you work with the cut and try method, you have to do everything again. Here, not, because everything is there. You can use it and you can change the elements, and that is an element which is important. It does not answer your question, but I think maybe it's part of it, because this can, with artificial intelligence, you can run this in such a way that this kind of questions can be answered almost automatically. I don't know whether this is a satisfactory response. I never used artificial intelligence with this, so I have no experience.
So a bit above word could be useful.
My answer?
So sorry?
Okay, so I told you, I think you can combine this, you can use artificial intelligence and use this as a method, a computation method in artificial intelligence. I think it would be interesting to do that for complex systems like operation amplifiers, where this method, it becomes rather tedious. It's a lot of work to do it. But if you combine it with artificial intelligence, I think you might come up with an interesting answer. I believe in this more than in and then you apply the method and you have some people are developing nowadays. I know there's a group in Egypt who is using this method, trying to develop a tool for design. But again, it turns out to be a kind of ready-made tool. You're there and you don't have to know anything about what you do. You just pick there and the program is doing everything. I think using artificial intelligence would be a much more interesting way to approach this.
Okay. I think it is a really interesting answer, and that leads for many grounds for future research. The next question is from Ayub Aitida from IMS Laboratory. For high frequency application close to FT, what are the alternative methods that can be used to design the transistors?
I will repeat the question because I'm not sure I understand it. My interpretation is FT is the upper boundary, And how do we work if we have values, frequencies to consider which are beyond FT?
Not necessarily beyond, but at least close to the FT value.
Close is not a problem. If you use FT over 10 over 5, it's okay. But don't go as far as FT, because then the results that you're going to get are no more correct.
Okay, so
it's a limit.
The question was about also different if there was alternatives to be near these frequencies.
No, the method is based on the fact that you have parameters. Parameters means a model. A model is the QSM model. QSM means you can't expand this model beyond the limit. If you go to higher frequencies, then you know that you're going to have excess phase. You're going to have a resistive component in the input impedance of the gate. It's no more a pure capacitance. It's a resistance and capacitance in series. You have to go really to scattering parameters, but that is really very, very high frequency. If you work with a 20 nanometer technology, the FTs that you're going to consider, they are already way above 100 megahertz. There are a few hundred megahertz. So it all depends. If you come up with a circuit that works at 1 terahertz, yeah, okay, 1 terahertz, just go to scattering parameters. You will not work with this.
Okay.
But I think the field of circuits that where you can apply this method is already very, very large. Yeah.
Right. And we have a last question from Jan Deval. Sizing is linked to matching for small gate lengths. As matching is critical for analog RF circuits, can we jointly size transistor and take matching into account with the proposed optimization?
The answer is yes. Yes, but I did not speak about that, but it's in the book. So the method is extendable. You can use you can do that. Yes, it's there is a chapter. If you want, I can. I think it's chapter 5. Is 4 or 5 is dealing with this aspect. In fact, it consists simply it is an extension of the lookup functions, which and you work with these extended lookup functions. There are a few examples in the book. Yeah, works.
All right. And lastly, not a question from the live chat, but more from me. It's more a question about a young designer. You detailed the workflow that you are using as steps, but I was more interesting also about the time and the proportion on each step between simulation and parameters and extractions throughout lookup tables. So how long and how different is a workflow with this new approach?
I have no exact figures. It's depending on your own skills or the way or how much you are accustomed to use the method. It represents an investment. You have to spend some time thinking about your circuit. How should I deal with it, etc. So I'm not going to say this is working at once. And I think this is one of the problems, because in many design houses, designers are under pressure. The stakeholders, they want everything to go fast. And so they're using the cut and try method, and they're going to continue using this. But there is a trend. I know that in California, this method is being used in a number of design houses, but it is you have to consider this as a kind of investment. When you are designing circuits and you know that you will have to review this circuit to store the data so that they can be used for other designs, etc., then it becomes interesting to have a thing like that, which allows you to enter directly in the problem without having to do all the work again from start from zero again. And so the answer to your question, I think, is yes, it takes time. If you are in a hurry, forget it. If you want to invest the time and really understand, and this is a point which I didn't mention, in fact, when you do it with the cut and try method, how are you sure that you get really the optimum? There are many, many optima possible sometimes. So I think for education, for instance, this method is a way to bring you back to what existed a long time ago. A long time ago, students were designing with graphical characteristics of bipolar transistors, things like that. But they had values, and they learned a lot of things from that. Nowadays, we're working with literals, and we said, oh, your GM could be of the order of, let's consider this, and you always get the result. But the connection with the real circuit, you don't have it. Well, in education, maybe you say, I don't need it. I just want to know the principles. I think it helps you to see what are the order of magnitude. I think this is an experience as a teacher. I know that that is really one of the problems when you ask students what is the order of magnitude of the transconductance of a transistor, and this is a young student, sometimes you're amazed to hear what are the results. So again, this is a way to get closer to the reality. You're working with real values. You see what is possible, etc. That's another point. I don't answer exactly your question. Can you repeat what was the question?
No, I think it's answer it even more broadly. So I think it's a good answer for me at least.
Okay, thank you.
So I think it's over for question. We don't have any more question in the chat, so we will soon end. If no one has any more question, maybe we will wait 1 minute just for the last question.
I did not give my email address. I think I didn't give it. I will give it now if somebody wants.
Can link it in the chat. If
you have it, okay, good.
Yes, yeah. I have it.
I will come back. Just let me return to.
Here it's just linked in the chat.
Yeah, I'm coming back. Voilà. Votre présentation. Ah, c'est pas ça. Je vais. Okay. So, here, I see you again. Voilà. Okay.
Perfect. So I think since we don't have any more questions, we will end the live now. So thank you again, Professor Jesper, for your intervention. It was very instructing, and we are really glad to having you as a first talk for our new team. We are really proud of having someone like you at Bordeaux, even virtually.
Okay.
So
Drink your good glass of wine, Bordeaux wine.
I hope we will share the next talk with wine and cannoli. So don't leave the room now. I will shut the stream and we will have.
It was a pleasure. I thank you for the contact, and I wish the best for your student branch. And please don't hesitate to contact me if you have questions. So, bye-bye.
Bye.